Okay, greetings and welcome. Today we're going to be looking at related rates problems, specifically the ladder problems, and we're going to look at two variations of the ladder problem. So let's go ahead and get right into it.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relaxed one.
So related rates is a topic that has the potential to be quite difficult. The problems can they have the potential to become extremely difficult. And there are some introductory problems that are pretty common. The cone problem, this problem, the ladder problem, the spherical balloon problem. All of these are pretty common introductory related rates problems that when you first encounter them are still going to be pretty difficult. But once you're somewhat introduced, they're fairly routine, but there are variations to these problems which make them become much more difficult. And so today we're going to look at two variations of the ladder problem. The first will be the most common one that you probably normally see, and the second will be a little different. And we also in a part two video have a fairly intricate ladder related rates problems. But let's look at the first example of the type of related rates problem we're going to look at today. So I just want to read the problem, and it says a 26-foot ladder is leaning against a wall. The base of the ladder is falling away from the base of the wall at a rate of 5 meters per second. How fast is the top of the ladder approaching the ground when the ladder's base is 10 feet from the wall? So I just want to kind of make a sketch of this situation. So let's say this is the wall, and of course, this is the ground. And we have a 26-foot ladder leaning against the wall. So there's some ladder, it's 26 feet. And it says the base of the ladder is falling away from the wall at a rate of 5 feet per second. And so this is the base of the ladder here. And so the distance from the base of the ladder to the wall, let's call that X because it's horizontal. And also let's call this vertical distance here Y. Now it says the ladder is falling away from the base of the wall at a rate of 5 meters per second. So that's a rate. And on these related rate problems, you really want to take note of what's constant. What's a rate? Is a rate increasing or decreasing if it's not explained based on a scenario? So in this particular problem, of course, the ladder is a constant. No matter how it falls, the ladder is going to remain to be 26 feet. So it's a constant. Now, the distance away from the base, of course, is varying. And as the ladder falls, I think it's pretty easy to understand that the value of X is getting bigger. So therefore that rate is increasing as the ladder falls. And so when they say this rate is 5, we can say that dx dt equals 5. So the importance of knowing if the rate is increasing or decreasing determines if this number is going to be positive or negative. If it was interpreted that the rate was decreasing, then this would have been a negative number versus a positive number. All right, so let's see what else the problem says. So how fast is the top of the ladder approaching the ground when the ladder's base is 10 feet from the wall? So what it wants us to do, it wants us to find, so how fast is the top of the ladder approaching the ground, find dy dt. And generally these related rate problems happen at a particular instant, and we're going to find dy dt when x equals 10. All right, so that's the layout of the problem. So again, the basic things to understand is you want to determine what's a constant, what guys are varying. When they give you a rate and don't directly tell you if the rate is increasing or decreasing, you want to figure out if the rate is increasing or decreasing to determine if the number is going to be positive or negative. And then you figure out what you're finding at what moment. So we're finding dy dt when x equals 10. So when y'all have all that laid out, then you have to find a way to relate the rates. The rate that they're they're giving you with the rate that you're trying to find. So basically we need to find a way to relate X and Y. And if you look at it, this is a right triangle. So of course we're assuming the wall is standing perpendicular to the ground. And probably the most elementary way to relate X and Y would be with the Pythagorean theorem. So an easy relationship would be that X squared plus Y squared equals 26 squared. Now, once you find a way to relate, then you take the derivative with respect to time, plug in what you know, and solve for what you don't. So we're going to take the derivative with respect to t of this whole situation. And the derivative of x squared with respect to t is 2x dx dt. And derivative of y squared is 2y dy dt. 26 squared is 676, but it's a constant, and so its derivative is 0. And we can divide everything by 2 just to make everything nice. Let me move down here so I'm not too cluttered. And so we have x dx dt plus y dy dt equals 0. So, and now let's plug in what we know and solve for what we don't. So we're trying to solve for dy dt. And so we should be able to plug in for everything else but dy dt. So at this moment, and another thing to remember, if you're just, getting introduced to related rates, is you want to plug the values in for the variables, those guys that are varying, after you differentiate. Of course, if you plug those values in before you differentiate, when you take the derivative, you're just going to get 0 because you'll be taking the derivative of a constant. And so it's important to remember that you take the derivative with respect to t first of the variables and then plug in their values at this particular moment. So at this particular moment, x is 10. Dx dt was given to be positive 5. Y wasn't given, right? The value of y wasn't given. So we need to be able to figure it out. Well, at this moment, x is 10 at this particular moment. So we can easily solve y by Pythagorean theorem. And so if we utilize Pythagorean theorem, we'll find that y is 24. So at this moment, y is 24. And dy dt is what we're trying to solve for, and set that equal to 0. And so it's simple algebra here. So this is 50. We'll move it to the other side, and we'll get 24 dy dt equals negative 50. And then we'll divide by 24. So we should get, I'm kind of moving all over the place. We should get, I'm going to try to squeeze it in right here. I apologize. We should get that dy dt is negative 50 over 24, or negative 25 over 12 feet per second. So that actually is a solution. And when doing a related rates problem, when you get a rate, the rate should make sense in the context of the problem. So you notice the rate we received was negative. And again, if you look at it, as the ladder is falling, as the base of the ladder is going away from the building, from the wall, the vertical distance is getting smaller. So the rate is decreasing. So that's why we got a particular negative rate there. All right. Let's look at example number 2, a slight variation of this particular problem. So in example number 2, it says a 17-foot ladder is leaning against a wall. The top of the ladder is sliding down the wall at a rate of 3 feet per second. The ladder's angle of elevation, measured in radians, is the acute angle formed by the base of the ladder and the ground. What is the rate in radians per second that the angle of elevation is decreasing by when the ladder's base is 8 feet from the wall? Okay, let's look at another sketch of this particular situation. So this time our ladder is 17 feet tall. Again, that's a constant. I apologize, it's not the straightest ladder in the world. Maybe it got bent in the heat a little bit. Okay, it's 17. The top of the ladder is sliding down. So again, I want to designate, and this is right angle, as you know, designate this guy is X and this guy is Y. So the top of the ladder is sliding down the wall at a rate of 3 feet per second. So that's this rate. So dy dt is -3. Again, that's a decreasing rate there. And the ladder's angle of elevation measured in radians is the acute angle formed by the base of the ladder and the ground. So that would be this angle here. I'm going to call that angle theta. And it says, what is the rate in radians per second that the angle of elevation is decreasing by when the ladder's base is 8 feet from the wall? So it wants me to find d theta dt when x equals 8. All right. So once again, this is very similar to the situation in the previous problem. So we kind of know what are our rates and what are our variables. So, I mean, what are our constants and what are our variables? So 17, of course, the length of the ladder is a constant. This distance, y, x, and theta are all varying in the problem. And it's a similar problem. It's described as the top of the ladder sliding down, but it's essentially the same situation as when the base of the ladder was pulling away from the base of the wall. So we have a rate for y, we have a rate for theta, and we have a length for x. So we need to find a way to relate all these things. So primarily I'm looking at relating my rates. And to think about a way to relate y to theta, and again, this is the right triangle, it seems like sine theta would be a good relationship because sine is opposite over hypotenuse. So we can say, and I'm going to try to make this writing here a little more, not as crunched up as in the previous problems. We can say that sine theta is y over 17. And again, once we find a way to relate the stuff, then we take the derivative with respect to time. So we'll take the derivative of this junk with respect to time. A derivative of sine theta would be cosine theta d theta dt. And the derivative of y over 17 would be 1 over 17 dy dt. So they want us to find d theta dt. So let's see if we know everything that we need to find, if we can be able to plug everything into this problem. So cosine theta. So do I know cosine theta? Well, here's the triangle. Cosine theta would be adjacent over hypotenuse. And do I know x? Yeah, because at this moment, x is 8. So cosine theta at this moment would be 8 over 17. So I do know cosine theta. It's 8 over 17 times d theta dt. That's what I'm trying to solve for. Equals 1 over 17. And dy dt was given as -3. All right, so we can really get rid of those 17s, multiply everything by 17, if you will. So we'll have 8 d theta dt equals -3. And if we divide by 8, we'll get that d theta dt is -3 over 8 radians per second. So that was a slight variation of the typical ladder problem, but still pretty basic. Again, in our part 2 video, we have a very interesting and I might even dare to say intricate ladder related rates problem. So we'll stop there. I do want to make one mention of one thing before I stop there. So sometimes the way this question was worded, it asked at what rate was the angle of elevation decreasing. So sometime when it asks at what rate is it decreasing, they'll have the answer if you were doing a multiple choice problem, or even if you weren't doing a multiple choice problem. Since it already said decreasing, that gives you the liberty to write that it's decreasing at a rate of 3 over 8, meaning you can write positive 3 over 8 because that's the rate at which it's decreasing. Now, if it just said blindly, what rate is the angle of elevation changing at, then you would be obligated to say -3 over 8. But again, if it says, at what rate is it decreasing by, since it's already telling you the rate is decreasing, then you have the liberty just to put 3/8. A rate of negative 3/8 means it's decreasing by a rate of 3/8. But anyway, that was our ladder related rates problems. We will see you next time.
Specialize in science and mathing. Original black men. Busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction. Black thought, the infinite relax one.